to have you here. So he is PhD docking, and he's been hired into docking and speaking about turbulence that export radial conditions, mainly from the distillation point. So what's yours?
Thanks. Yeah, so I'll be explaining in a minute what all these words in the title mean, especially for the people who are not exactly from the plasma physics background. First, I'd like to note that this work relies very heavily on my co-authors. In particular, it has been recently published with Konrad Eder as first author, so he actually did the majority of the work, and I'm presenting on his stead as he is writing up his thesis. But I'll give more general introduction, etc. Yeah. So it's my first time at this conference, and I wasn't sure exactly what the background of the people will be. I was told that it's rather general for neutral fluids, etc. But I saw in the program that half the talks had turbulence in the title. Therefore, I decided that I probably don't need to introduce turbulence in general. On the other hand, I was not sure how much people are familiar with the boundary plasmas in fusion reactors, and in particular with reactive plasmas. So that's what I will spend the introduction on. I've seen or heard that last week you had some talks about the X-point radiator already, but I haven't seen them. So if it's too boring and if you are already familiar with everything in the introduction, tell me, I can skip a couple slides. Anyways, after this, I will dive into the turbulence simulations with the grid code, and I will focus on strongly radiating diverter conditions. And I will show you results about the impact of plasma detachment on turbulence and the impact of turbulence on chemical reactions and the detachment process. I have one introductory slide about turbulence in fusion devices. You've seen this dozens of times, but in case someone didn't, here is a very nice turbulence simulation. Everyone shows from the WZholobenko code. You see these small-scale vortices in a single toroidal plane, and notice how in the toroidal direction they wrap up around the torus, forming these very elongated structures. So turbulence in magnetized plasmas is extremely anisotropic. The transport along the magnetic field is much faster than perpendicular to it. And the reason that we get this turbulence is that we require gradients in the plasma. We need the plasma to be around 110 million degrees Celsius in the core of the device to trigger the nuclear fusion reaction. While in the outside, the plasma needs to be roughly at room temperature because it has to be in contact with the walls at some place, and we don't want to damage the walls and damage the plasma. So we need at least a temperature gradient. We do not necessarily need a density gradient, but we'd like to have one. If you want to discuss this, we can. And this temperature gradient will drive instabilities, will drive fluctuations in electric and magnetic fields, and this will allow the plasma to escape collectively the confining magnetic field. Okay, so this is how a radial. Okay, weird. This is how a radial profile of the plasma pressure looks like, roughly. It's high in the center, low in the edge. And essentially, the gradient, which the pressure gradient, which we can sustain, defines how large the machine needs to be to produce fusion energy. There is the low confinement mode, and okay, the topic of the conference is boundary layers. So often people think of the confined plasma edge when they think about the boundary layer in a fusion plasma. And this is particularly prominent because their turbulence very often, at least in experiments, in present experiments, can be suppressed, which results in much steeper gradients, and this elevates the confined energy for the whole machine. And the fusion product goes nonlinearly with the so-called H factor. So it improves the fusion performance dramatically. It has major economic interest. Me, however, I will mostly focus on the region outside of the confined plasma, the so-called scraper flare. This is where the magnetic field lines do not close on themselves anymore before they interface with plasma-facing components, with walls, etc. But of course, the two regions cannot be separated. They are very close to each other, and mostly heat and particles coming from the edge going to the scraper flare. In particular, importance for the survivability of plasma-facing components is the fact that the steep pedestal here in the plasma edge also has drawbacks. It can trigger magnetohydrodynamic instabilities, so-called ELMs, and these will transiently put very high heat and particle loads on plasma-facing components. You see here a picture from such an event in the MAST Stockhammer. So we would like to understand the turbulence suppression in the edge, but we would also like to be able to destabilize turbulence a little bit, because we would prefer it compared to the macroscopic instabilities like this. Now, when you look at radial profiles, people often underestimate how large the plasma boundary actually is. This is a two-dimensional cross-section on a colloidal plane. You see here again the confined region, the plasma core, and then the black line is the separatrix. It separates the confined plasma from the scraper flare, from the diverter. And in the scraper flare, the plasma flows through the target plates. And the separatrix is created intentionally by additional toroidal field coils to direct the plasma flow away from the confined region into the separate diverter region. So this allows to better compress impurities and neutral gas into the diverter and away from the confined plasma. We don't want impurities in the confined plasma in particular. And the neutral gas compression allows for better pumping. I'll talk about neutral gas in a second. And notice how here the plasma edge and the scraper flare take up a significant fraction of the magnetized volume. That's because when you go further radially, the circumference increases. Okay, another picture of the scraper flare. Even without edge-localized modes, heat fluxes to plasma-facing components are a major concern for fusion reactors. The reason for this is that the heat-carrying channel in the scraper flare tends to be extremely narrow, in the order of a few millimeters, which yields around 2 square meters of plasma wetted area. And when we project the heat fluxes that we expect in a reactor onto this area, we get to very high heat flux densities, which are beyond material limits. So material limits for water-cooled tungsten are 10 megawatt per square meter. If you surpass it, you melt your tungsten. We don't want to do this. The difficulty arises basically because we have the confining magnetic field, so the perpendicular transport is slow, but the transport along the magnetic field is fast. And so this results in this exponentially decaying heat flux with a very small decay length. And what this shows us is that even without edge-localized modes and other difficulties, the plasma needs to be in a detached diverter condition. So 90% of the heat flux, or up to 90% of the heat flux, should be radiated away before hitting the target plates. Before I talk about radiation and neutrals, I wanted to make a small note about some fundamental difference between the plasma boundary and boundaries in neutral fluids. This, I think, aligns very well with the talk you have seen just before the lunch break. In neutral fluids, the flow near the wall tends to be very small due to friction with the wall. In plasmas, it's the opposite. In plasmas, the flow along the magnetic field in particular tends to be sound speed into the wall. So we have an acceleration of the plasma into the wall. And the reason for this is that the plasma consists of charged particles, electrons and ions, illustrated here, and they have a very large mass difference, which means at similar temperature, electrons move much faster than the ions, so they would escape faster into the wall. They charge up the wall negatively. And then here you see a figure illustrating that very close to the wall, there is a buildup of positive charge in the plasma. And this, in steady state, leads to an electric field into the wall, accelerating the ions and holding the electrons back, which then allows the remainder of the plasma to be quasi-neutral. Yeah, so we have very slow flows in neutral fluids near the wall, but in the plasma, they are very fast. And then when the plasma hits the wall, it recombines into neutral gas. So electrons and ions, they undergo surface recombination. They deposit their binding energy into the wall, heating it up, and they come back as a neutral gas. Showing this mathematically, it's this simple equation. So the flux of the neutrals out of the wall is equal to the ion flux into the wall, and the ion flux will go at sound speed with some recycling coefficient. This coefficient actually hides a ton of physics, in particular related to surface chemistry. The ions can be absorbed by the wall, they can desorb, they can be reflected, etc. Some of the neutral gas is pumped out, but roughly 99% of the ions come back as neutrals. Then when they go back into the plasma, they are ionized by the electrons in the plasma. This takes the kinetic energy from the free electrons to overcome the binding energy. So this cools the electrons, putting the bound electrons into the plasma. It's dilution cooling. Then below essentially binding energy, we get multi-step processes. So before an atom is ionized, it's first excited, then it can emit radiation, etc. So we get additional cooling due to radiation. And below 1 electron volt and at high densities, electron and ions can recombine volumetrically into neutral gas. And this is shown by these rate equations. Yeah. So we have a cycle. The ions and the electrons, they flow to the wall, they recombine into neutrals, they come back as neutrals, they get ionized, they flow back to the wall. So this whole process is called recycling. This is what sustains the plasma density. So the total density of ions and neutrals is more or less constant, up to pumping and pumping of fresh gas. And it's a process which cools down the plasma while heating the wall. So it needs to be sustained by heat coming from the center of the fusion device. And if the temperature falls below a certain threshold, around 1 electron volt, the plasma can recombine volumetrically. And this is in fact what we want to have, because what I was showing you before, the transport of plasma perpendicular to the magnetic field is limited, so we get these very narrow heat carrying channels. However, when the plasma recombines into neutrals, first it emits radiation, and then also the neutrals, they don't care for the magnetic field. So this spreads the heat much more isotropically over the plasma facing components. And here are some pictures which illustrate the process. This is the ionization rate distribution in a diverter. The white line is the separator. The diverter is down here. The neutrals density peaks at the diverter, then they propagate some direction inside and decay. Hence, you have this distribution. And the upper figure is along the magnetic field. So when the heat and when the plasma go into the diverter, due to deionization of the neutral gas, the plasma density increases, the temperature drops. And when the density increases sufficiently, it can fall off again due to recombination. Right. This is the temperature dependence of the rates. The ionization rates has roughly this exponential behavior. So it's high plasma temperature, electron temperature in particular. We will have no neutral gas in equilibrium. We will have a purely ionized plasma. Then below 1 electron volt, recombination takes over and the plasma can recombine.
Very stupid. Your picture there is the wall not getting more and more charge.
No. So there is a tiny charge of the wall with respect to the plasma. And it's just big enough to create an electric field into the wall, which leads to the ions and the neutrals traveling at the same speed to the wall. So this is what keeps the plasma quasi-neutral in total. Okay. Right. So in thermal equilibrium at 1.3 electron volt, we would have equal electron and ion densities. And then below that, we would have a recombining plasma, above it an ionizing plasma. But what you see here is a third process, charge exchange, which is much larger than all the others because it is resonant. So what also happens in the plasma is that the bound electrons, they do not care. They can just hop from a neutral to an ion. and they end up in the same atomic and energy state, so it's a resonant process. But the neutrals and the ions in this process, they swap their velocities. And this leads to a fast equilibration of the neutral and plasma flows and temperatures in places where the neutral density is high. This was all without molecules, and this is sufficient for the talk. I just wanted to point out with this pretty picture here that the reality of plasma chemistry is much more complicated. I haven't said more than a sentence about surface chemistry. There are molecules, there are all kinds of molecular interactions in the plasma, but more or less the discussion about the ions is enough. There is one more ingredient which I will need for the talk, and this is impurities. So apart from deuterium, ions, and neutrals, which we want to have for the fusion reaction, there are other species which can end up in the plasma. And this is interesting because they have very different cooling potentials for the plasma. You see, this is a logarithmic scale. Tungsten, for example, is very difficult to ionize. So even at very high temperatures, it can radiate a lot in the confined plasma. We do not want to have it because it leads to cooling. So in the core plasma, we want to minimize the impurity content. However, in the diverter, we can actually mix additionally in some light impurities like nitrogen or neon, which will help to cool down the diverter because of this cooling factor. Okay, so far I've been talking only about chemistry. Most people here, as far as I can judge, are interested in turbulence. So finally, I have to justify why I was telling you all of this. I'll do this with some numbers. So we simply evaluate the terms in the continuity equation to judge their relative importance. We have here the plasma continuity for the plasma density n with radial and parallel transport. There is a source term on the right due to the ionization of the neutrals, and there is the neutral continuity. And these are some typical parameters in a diverter. And then what we find is that the normalized ionization rate with the neutral density in thermal equilibrium is 6 per second. So it's this is the time scale it takes for ionization to change the plasma density by a factor 2 or so. And then if we look at the other terms, we find that they are much larger. The parallel streaming, for instance, we can estimate with sound speed and the connection length from the diverter to upstream. Okay, the turbulent transport I've taken out of one of the simulations, and the neutrals are also very fast because they don't care for the magnetic field. So all of these are orders of magnitude larger. And what this means is that the plasma and the neutrals will be transported from one place to another before reaching any thermal equilibrium. And the state of the plasma, the ionization degree, will be determined non-locally. So we need to solve transport together with the reaction processes. At the same time, turbulence in the plasma edge and scraper flare in particular is non-local itself. We cannot distinguish or separate it from the mean flow. So we will need to simulate turbulence together with the reactions. Now, before doing this, I should point out that these simulations are becoming possible only now. They are very challenging. So the workhorse for the diverter design in upcoming fusion reactors have been so-called transport codes, like SolPS, SolH3X, etc. What these codes do is you can define a plasma diffusivity like this, and you can plug it into the continuity equation for the mean plasma density. And then you can forget about the physical mechanisms behind the diffusivities. You can just take them as constants. So the transport is prescribed in these codes. However, they have very elaborate models for the parallel transport in the scraper flare and for all these reactions, including molecules, surface chemistry, etc. So they are very useful. But as you see in this figure, the transport is difficult to fix or predict. So to match the experimental profile here, these are the red triangles. The SolPS simulation, the blue line, needed to prescribe the transport coefficients written here in green. And notice that the vertical scale is logarithmic. So the diffusivity needed to be varied by more than an order of magnitude, which makes it difficult for these codes to be predicted. Right, and with this, I would like to transition to turbulence simulations using the Grillix code. You can compare this by eye with the GZholobenko simulation you just saw. Well, I noticed you won't see that much on the projector. You do see some small-scale structures and the very elongated structures in the toroidal direction. You might notice that the core is empty. We do not simulate the plasma core, just the action scraper flare. Okay, with this, I will move on. The way we do these simulations is we are using Cartesian grids in each colloidal plane. So we are very flexible in terms of geometry. However, because the plasma is very anisotropic and the power motion is fast, we want to have a sparse grid along the magnetic field. And we do this by field line tracing and constructing locally field line coordinates for every grid point. And this allows us to carry out very highly resolved turbulence simulations in the X-point region, which is interesting for things like the X-point radiator. Just a brief mention, the Grillix code I'll be talking about is a fluid code. Many people in here are working with gyrokinetics, so if you would like to do something like this gyrokinetically, you might be interested in the GNX code. This is developed in tandem with Grillix. We share a lot of the numerics infrastructure, but GNX is a gyrokinetic code. We have a very close exchange. So you see here a simulation with GNX, also in the same Astex upgrade geometry with the diverter. So far, doing gyrokinetic simulations at high collisionality has been difficult, hence why I'm doing this with the fluid code, but we are working on bringing these together. You can ask me if you're interested. The Grillix code is a fluid code. So basically what we're doing is solving fluid equations like the continuity equation for plasma density, equations for electron and ion temperature. You have the question? How we impose them or which boundary conditions we impose? Okay. There's a ton of boundary conditions. Let me go very quickly through the equations, and then I'll tell you what we do with each quantity. So we have the equations for plasma density and temperature. On the wall, we force no flow. So perpendicular to the magnetic field, we force no flow. There is a finite flux surface through which the plasma cannot pass. And at the diverter, we have floating boundary conditions, so the densities and temperatures can adapt. Then we have the parallel motion. Okay, these are drift fluid equations. So the perpendicular flow is not dynamic, but it's assumed to be quasi-static, given by the E cross B diamagnetic drift and polarization. And this is important. You see in the polarization here, we have the ion inertia. So this is what will be driving the turbulence. But this is obtained through an expansion. So we have the E cross B nonlinearity and not a dynamical perpendicular velocity. The parallel velocity, however, where is it written? It's not written anywhere. Okay, so the perpendicular velocity is given by the drift, but the parallel velocity is free. And for the parallel velocity at the diverter, we force it to be sound speed. Okay. And then we have a quasi-neutrality condition, which forces to have no charge accumulation in the plasma, which forces all the currents to balance. This can be written in vorticity equation, but I haven't done it here. So we also have a boundary condition for vorticity. The code is electromagnetic. We have not just the electrostatic, but also the electromagnetic potential. Acting non-linearly also through all the parallel operators. All right, that's the plasma model. Yeah.
The way you write it, it's like the polarization would add back I and D. That
yes, polarization is also. That's a very tricky thing. So in reality, the polarization would be part of the total velocity, so it would also add vectorings. However, this is obtained through an ordering, and the ordering assumes that the divergence of the different flows is similar, but the polarization flow itself is smaller than the others. So in practice, we do drop the advection by polarization. We just keep polarization is important because it enters the current conservation. There it's important. Okay, and then the main thing, yeah.
Again, my question is this: your boundaries are not simple, right? They are carved boundaries.
Yes.
So how do you impose the boundary conditions? Say, even if you want to impose a no slave, or when you say we impose sound speed, how do you do that?
That's a very good question, but I probably do need a couple minutes to answer it. We use penalization in practice to deal with the complicated shape of the boundary conditions. Not sure if you're familiar with immersed boundary technique. Yes, we're using immersed boundary. Okay. And if you want to know more, I have some backup slides, but we'll need some minutes to get through them. All right, and finally, I can tell you something about the neutral. So this is a very simplified view about the plasma model. I didn't intend to spend too much time on this. If you want, you can ask me questions, more questions afterwards. But what's important is that the plasma is coupled to the neutral gas. There is the recycling boundary condition implemented, so the plasma that flows out at the diverter comes back as neutrals. And then the neutrals undergo a diffusion equation with the diffusivity given by the charge exchange reaction. So we assume that the neutrals mostly scatter off from the plasma due to the charge exchange. And then there are the ionization and recombination rates. That's a one-moment neutrals equation. I'll show you a three-moment equation set in a minute. And with this, we can run simulations like that, if we can. No. Okay. That's the PDF. Okay. That explains a couple of things.
And
All right. I have to admit, I'm not sure how much you'll be able to see from the projector. So those who can might want to focus on the monitor instead. What you see here are ion temperature fluctuations in a single toroidal plane evolving as a function of time. So that's from a gridlock simulation. On the projector, you don't see many of the individual vortices because I have this the very brutal color bar. It goes from minus to plus 250%. And the goal was to show that we have very high fluctuation amplitudes in the scraper where you will see some filaments that really reach beyond 200%. These are called blobs because at the outward midplane. So in this cut of the simulation, they appear roundish. You might notice that at the diverter, for example, so here, the filaments are very elongated. This is because of the magnetic shear. The magnetic field is very non-uniform, and it will force the structures when they propagate along the magnetic field to take this form, which is actually beneficial for turbulence control. And I guess particularly if you look at the monitor, you will notice that the plasma also rotates in opposite directions in the confined region and in the scraper flare. So there is an E cross B flow. Part of it is a zonal flow. There is a mean flow component. Some people might be interested, but it's not critical for this talk in particular. What I want to show you here is the quantitative. Yeah.
Right.
Yeah. Yeah. So these are fluctuations, and they can arise anywhere. And experimentally, they also see turbulence in the private flux region. However, the red region here, which shows the diverter, there we have the immersed boundary technique. So, well, similar as in Gisela, the transition to the boundaries is smooth. It's not at a single surface. So this is why the structures really appear to be coming out of the boundary because they're produced in this region. It's not a very sharp boundary, let's say. There is not a super sharp region there. which also allows us to get away with an isotropic grid resolution, not refining it near the boundary. Right, back to the neutrals. So quantitatively, the neutrals are important because they sustain the plasma density, they also cool the plasma, and so they provide these key sources without which we cannot match even the background plasma profiles. You see a comparison of a simulation with and without neutrals. These are profiles at the outward midplane. So if I go back, it's a line here at the outside of the tokamak. Okay. The black line shows the experimental measurements. It's from integrated data analysis from multiple diagnostics. And then you see that the red line with the simulation with neutrals is the one that matches the experiment. And this is because it has a realistic source due to the neutral ionization here. And the temperature is cooled down, and also the heat transport is changed because the neutrals, the plasma density has changed. What we were doing without neutrals is that we were sourcing the plasma simply at the core boundary of our simulation. And then in the scraper flare, the plasma flows out and we get super low densities there and we get a very steep gradient. So that's the main reason why we want to have the neutrals. The same picture we find also at the diverter. This shows the high field side on the left and low field side on the right in the diverter of the tokamak. Again, density and temperature. And you see that without the neutrals, we were underestimating the density compared to the experiment by an order of magnitude and overestimating the temperature. But the neutrals increase the density, decrease the temperature, and we get a much better match. Also, when you increase the density and you decrease the temperature, you increase the collisionality, which is very beneficial for our fluid model. What I've been showing you so far was in L mode, so low confinement conditions. The reactor relevant conditions are H mode. So recently we have done a validation also in eta baseline H mode conditions. Basically, we also see a very reasonable match here, both for the electron density and temperature. And in H mode, we also had ion temperature measurement as well as radioelectric field measurement, and we matched those quite recently as well. So the model does what it's supposed to do. With this, finally, I'm set to talk a little bit about X-point radiator detached diverter conditions, and I will start with experimental findings. So as I stressed in the beginning, a reactor will have to operate in detached plasma conditions, so the plasma recombining volumetrically before reaching the diverter and a lot of the energy radiated away to reduce the heat loads on the plasma-facing components. When going to these strongly detached regimes, historically it has been difficult to control them because they would tend to move into the confined region and lead to disruptions. But with feedback control, with modern control techniques, this has become experimentally possible. And this figure here is a visible camera image of the diverter radiation. You see in magenta the alpha radiation, so hydrogen radiation from the diverter. And then the radiation in blue, which is above the other one, is really at the X point. That's the X point radiator. And it radiates away more than 80% of the heating power. When you do a tomographic reconstruction, again, you find that the radiation really sets above the X point. This is why it's called an X point radiator. So the plasma starts recombining and radiating in particular quite early, way before reaching the plasma-facing components. And then experimentally, it was also found that this can have pretty good confinement properties still. And if the radiator is pushed a little bit into the confined plasma, we get rid of edge-localized modes because we destabilize the turbulence and we somewhat decrease the pedestal. That's what we want to understand with our simulation. For some basic understanding, it's difficult to read, I suppose. For some basic understanding of the mechanisms, you can use an analytical two-point model, no differential equations needed. This has been published by Ulrich Stort, and this was a very important guidance also for our simulations. So basically, the two-point model just looks at what happens from a point upstream, so at the outward midplane, where we imagine most of the radial turbulent transport to sit. And then this point is connected along the magnetic field into the X point region. The blue line is one flux surface and the black line is the separatrix. And what this shows you is the flux expansion in the plasma edge. So creating the separatrix and the diverter geometry increases the magnetic volume between two flux surfaces in the X point region compared to upstream. And this is a key ingredient for the radiator, because what this allows you to do is to radiate much more energy with a lower impurity concentration. So because the impurities can fill up this whole volume and radiate there, but for the confined plasma, this actually takes very little volume in terms of how many flux surfaces you use for this. Right. And then the next ingredient is the impurity. So the neutrals, as I was saying before, are radiating mostly only below 10 electron volts, and you somehow need to get there in the first place. And for this, you need impurities. Well, it's you need both. In Aztec upgrades, nitrogen is a very good radiator, and in the coronal equilibrium, its radiation coefficient looks like this. So it rises very sharply, and it's large between basically 2 electron volts and 20 electron volts. So 20 electron volts is still a lot. Usually upstream we have 50 or more. But the important insight from this model and looking at the radiation rates is that in this window, the impurity radiation is so large that the impurity concentration doesn't matter. What happens in practice is as soon as the plasma gets to 20 electron volt, it radiates all the energy away and it just goes to 2 electron volt below the threshold for impurity radiation. So this is why we use also this very simple model in Gridix. However, you do need to get to these temperatures, and for this you need the neutrals again. The model assumes that the energy conducted along the flux surface into the X-band radiator region will have to be dissipated by ionizing the neutrals and charge exchange. So this will dissipate both electron and ion energies, and this is what triggers the radiation at some point. So while this analytical model is useful, it assumes some fixed parameters, in particular upstream densities, temperatures, and the neutral density at the diverter. So to be fully predictive, we still need simulations. But this has motivated us, for example, to adapt this very simple impurity model. We do not solve for impurity transport. We are just fixing 5 to 10% nitrogen concentration just for the radiation. However, since the analytical model assumes that charge exchange cooling is important and also flow regulation by neutrals is important, they've extended the neutral gas model to 3 moments. Essentially, the parallel velocity moment for the neutrals allows for different velocity than the ions, and the temperature or pressure moment allows different neutrals and ion temperatures, which allows the neutrals to cool the plasma in the first place. But for impurities, we just use the simple model.
Can there be parallel direction for neutrals?
Very good question. So the neutrals themselves do not see the magnetic field, so they would diffuse isotropically. However, the typical assumption is that the main reaction in fusion reactors is charge exchange. So even though the neutrals do not see the magnetic field, they will swap places very frequently with the ions, which do see the magnetic field. And so effectively, the neutrals will obtain something like a parallel velocity. Okay. A comment about the temperature. So the assumption of high charge exchange is very good for the background plasma. You see here the ion temperature and the neutral temperature distribution, and they are roughly equal if you would average the fluctuations away, but the fluctuations are different. So the neutrals, the charge exchange is not fast enough to have to make the neutrals have the same temperature instantaneously, which is actually a problem for the fluid closure, and hence that kinetic effects are important for this. But we will continue nonetheless. And finally, the simulations. The details are published in this paper. Well, not published yet. They are on arXiv and being reviewed right now. We have 3 simulations: no X-point radiator, low X-point radiator, high X-point radiator case, which have a fair distance of the radiation front from the X-point. You see here a comparison of the simulations with the experimental data. The experimental data are very scattered, so these are raw data. Particularly for the temperature, I would say we get a very good match. For the density, the high X-point radiator case has a similar form as the experiment, but it appears radially shifted outwards. This might be due to experimental uncertainties, but yeah, more or less it's a reasonably good agreement with which we can live. Here you see a movie in the low X-point radiator case. So it's not enough for the neutrals to recycle to trigger the state. It's a transition that you need to enforce. Experimentally, there are 2 ways. You can do this with impurity seeding and then feedback control on the impurity seeding, or puffing of the deuterium. And because we have a fixed impurity concentration in the simulations, we are putting a gas puff in the simulations. And this is able to trigger the radiator, so this allows the neutrals density to increase and to penetrate into the confined region. And as you saw in the analytical model, you need a high neutrals density to get into the nitrogen radiation region, so to say. Then at this point, the gas puff can be turned off. The radiator remains stable on its own. That's also observed experimentally and in other simulations. And what you see is a state where the plasma density is an order of magnitude higher in the radiation region than at the core boundary of the simulation. And the temperature is very low. It's below a couple electron volts. And on the left, this figure here shows the colloidal profiles of the electron temperature. So as a distance from the X-point, 0 is the X-point. And you see that we have very strong colloidal gradients. At the outward midplane, the electron temperature is still between 30 and 50 electron volts, but then it drops to between 0 and 10, depending on the radiator height at the X-point. And I hope you see it. The arrow bars indicate fluctuation amplitudes. You see very nicely in the low X-point radiator case, the center case here, that the arrow bars in the X-point region are of order 1. So the fluctuation amplitudes are around 100%. And this triggers some interesting dynamics. Okay. So as I was saying in the beginning, the workhorse for diverter design so far are transport codes. So what we did is to compare our simulations with SOLPS results obtained a couple of years ago. Here you see the ionization, recombination, and nitrogen radiation rate in SOLPS. And here are the results from Grillix, and I would say they are qualitatively fairly similar. In particular, we get so the color scale is the same, so we get realistic distribution and size of the reaction rates. But in Grillix, of course, we are solving this together with turbulence, so we also get the fluctuations, which on the previous figure have been averaged in time. Now you could have noticed that the radiation front here is somewhat lower than in the SOLPS simulation, because that's the low X-point radiator simulation. We have also the high X-point radiator simulation, where the radiation front sits somewhat higher over the X-point. It's another thing that I would like to point out here. I'll say more about it later. But so in SOLPS, they use a fairly coarse grid. You see the really individual grid cells. And if you look closely, you would find that there is this ionization front, and the recombination front sits just below it. However, in Grillix, because we have these 100% fluctuation rates, the plasma locally goes from recombining to ionizing conditions. And the ionization and recombination fronts are really sitting at the same location. Yeah. So we have these ionization mantles surrounding recombination cores, where the nitrogen radiation is also low, but they are moving around, fluctuating in time. They do form these stripes on average. This is again the radiation, but on a linear scale. So it's the same data, just plotted linearly. And here we want to compare it to experimental bolometry measurements. The white lines are lines of sight. There are the FLX and DLX systems. Don't ask me about the technical details. Important for us is that the FLX system measures quantitatively, while the DLX system only measures relative radiation intensities. And what you see here is that for these different channels, for the high exponent radiator case, we get a very good match actually. And also the shape of the radiation appears fairly realistic. Okay, and with this, I would like to transition to my last part, the impact of turbulence on detachment and vice versa. So first, the effect of detachment on plasma flows. Without these detachment fronts, you would assume to the zeroth order that the potential, the electrostatic potential is a flux surface function. So you have colloidal flows, but no major radial flows. Then when you have this cold and dense plasma spot moving into the confined region, you get a vortex cell around the separatrix here. And then the high exponent radiator case, it has moved into the confined region. So the strong colloidal gradients in plasma density and temperature and the high resistivity allow for colloidal gradients of the electrostatic potential and for stationary vortex cells. And then if we want to quantify how much transport occurs due to these, we look at this flux surface line out highlighted here in green. And what we find is this is the radial particle transport along the line out. So further away from the X point at the outward midplane, you see this fluctuating particle flux. That's just turbulent transport. And then the vortex cell is here around the X point. And note that the y-axis is logarithmic. So the flow, the amplitude of the flow around this vortex cell is actually an order of magnitude larger than the turbulent particle flux. But it's a vortex cell, so it goes in and out and it cancels to some degree. And we found that it's highly parameter dependent whether the net transport is inward or outward. So these have been so far L-mode simulations, but we can ask ourselves whether this could explain the L transition in H-mode conditions because you have this additional transport channel. Then we can look at the effect of detachment on fluctuations. You see here instantaneous snapshots of density and electron temperature fluctuations. The color bar goes again to 200% and it's saturated in the detached cases. So you see that in the region around the radiator, the steep gradients trigger very large fluctuations. And looking at it more quantitatively, we can have a look again at this magenta line out here. And we can count turbulent fluctuation statistics in this region. And what you see is that without the exponent radiator, that's the blue line, we have more or less Gaussian statistics. So there is more or less symmetric distribution of fluctuations around the mean, and it's around 20 to 30% fluctuation amplitude. But then going to the detached cases, we get very high fluctuation amplitudes, actually about 500% of the background, but these are rare events. So we have very high intermittency and the fluctuation distribution is strongly skewed. It's not Gaussian. So the most probable density and temperature are below the average. And what, yeah. On the left is written, yeah, it's written here. On the left is the density, on the right is the electron temperature. So it's for the ion temperature, for instance, you also have fluctuations which are comparable to this, but I'm just showing this. Okay. And then the final question that you could ask is, in presence of these very high fluctuations and turbulence, how does the turbulence affect the detachment process? And one effect in particular, which has been postulated more than 15 years ago, so by Sergei Krasheninnikov, Yannick Marandé. There have been solid simulations of this. They have found theoretically that, of course, the reaction rates are nonlinear. So there is a difference whether you evaluate the reaction rates at the average density and temperature, or you average the reaction rates themselves in time. And the version at the top, so for average density and temperature, this is of course what is done in the mean field codes, which solve for those quantities. And in the turbulent simulation, we get fluctuating as ionization rate, and those two do not have to be equal. So the fact that this can occur has been realized fairly early, but the simulations of turbulence detached conditions are becoming possible only now. I think Patrick Tomain was showing some of these last week. So only now we can quantify how large this effect is. And it's expected to become substantial below 10 electron volts. This is where the reaction rates have the highest slope. And also, of course, for large fluctuation amplitude. And here are the results. So on the left, in the top figure, I show the average ionization rate. And on the right, I show the ionization rate for average densities and temperatures. And you see that the two are quite different. We can look at the difference or the ratio, and we find that they are a factor 2 different. So the average ionization rate is a factor 2 lower in the simulation than the mean field ionization rate, which means that the neutrals penetrate deeper into the confined plasma than you could expect from the mean field model. And also, without the fluctuations, we would not have any recombination in the Grillich simulations because the average temperature stays above 1 electron volt. However, the fluctuations fall below. So we have less ionization and more recombination, and this allows in total for higher neutrals densities and easier detachment. The radiation, on the other hand, is 30% lower than in the mean field evaluation. But because the radiation has this fall off to both sides, so it falls off to small and to large temperatures, it really depends strongly on the parameters whether you get more or less radiation. So we cannot make a general statement about this, but for the ionization, it's clear that quite generally you would expect lower ionization rates than in the mean evaluation. And with this, I would like to conclude. So I hope that I've convinced you that neutral gas is essential for turbulent simulations in the edge and scrape-off layer, and particularly in detached conditions, as you would expect when the reaction rates are large and very important for the plasma. We get very strong gradients, we have high fluctuation amplitudes, and we have very strong interaction between all of these processes, the turbulence, the detachment, and the transport. Yeah, on the other hand, we have reasonable match with the experimental measurements. So we hope that with these simulations, we can actually soon be able to make predictions for fusion reactors. Thank you for your attention.